So Unit 1, kinematics. This is, we're going to start looking at motion now. The motion. It corresponds to chapters 2, 3, and the first part of Unit 4, or Chapter 4, in the Hewitt book, which is the book that we're supposed to use. Part A is going to go through constant speed, motion with the constant speed, and it'll be for the first couple activities that we do in the classroom. First off, many of us have a great understanding of what distance is. Many of us would be able to answer the question, how far is it to, say, Jordan? Some of you might answer 7 miles. Some of you might answer, about 10 minutes, 5 if you're speeding. Now, one of those answers is a distance answer. The other one is a time. And that kind of comes down to where in the country I think sometimes we are from, or we live at, is how we make those measurements. Do you measure things in time, or are you making those measurements in actual distances? And so the distance would be the 7 miles. The time part, about 5 to 10 minutes, is because of the area that we live in. Because sometimes things might be a certain distance away, but it's not always a straight path. Or there can be traffic getting in the way. And so that's what we look at is, or, how far do you live from the school? Some of you might say, it's about 2 miles. Now, that in itself tells us a distance, but it doesn't tell me in which direction to go for those 2 miles. And if you Google map to a location, it gives you turn by turn where to go. It doesn't just say 2 miles northeast. That would be more of a how the crow flies, so to speak, using that term. That is the displacement. The displacement is the distance with a direction, but it's the shortest path. And so that's the important part of that. It's the shortest path. Distance just tells us how far. Displacement tells us how far in what direction, but it's the shortest path. If you're able to, cut through people's yards and run straight across 169 but not playing Frogger. Things such as that. General speaking terms, distance is what we always use. Displacement is a new term for us. Displacement it's not an extreme weird term, but it is a newer term because it is distance, but it's distance with a direction. And that is where we get confusing. In our everyday talk, you're going to say how far did you travel, you're going to expect distance. I use the example, if I run the 2 mile in track, what would my displacement be?
0.
Displacement would be 0 because you started and stopped in the same location. The distance ran would be 2 miles. That would allow us then to really start getting into some philosophical debate. If you go down into the weight room and lift heavy things, did you do any work? Because if you lift it up and place it down, the total displacement would be what? 0. And the equation for work is force over a distance, or displacement. If you don't have a displacement, we all know that anything times 0 is 0. So did you do any work?
Sure feels like it.
It's saying that's where the two terms don't always work well with each other, because anyone who's been in the weight room knows you lifting weights up and down, it's work, but not by the term physics. Physics says no, but it's good work to do. And that's why when we get into talking actually about work, especially in my other physics class, I use the term work. Say it with more of a V instead of a W. And I even use a ERK and even spell it differently so that we can make that separation in our brain. Because I say work, most students would think, oh, going to work. Not the same. Physics work, real world work, not always the same thing. Sometimes they are. So that's the same thing when we get into talking about the distance or displacement, which one is which. And we have to be careful. So a couple extra terms that we're going to bring up is distance is a scalar measurement. Distance is a scalar measurement. You can think of scalar measurements as kind of things that you would have like in a bucket. Something you would measure in a bucket or a scale with, like you did over the course of last unit in the lab. Displacement is known as a vector quantity. A vector quantity is the shortest path between 2 points. And just like Despicable Me, the original, Vector was committing crime with both what?
Arms.
Direction and magnitude. Distance just has magnitude. Distance just has a number. Displacement has both direction and magnitude. And if you have to think about Despicable Me, feel free. Some would even say that displacement is essentially distance with the direction, and that's not too far off. We can add or subtract these displacements depending upon what they look like. And since it can be done in one direction, not the band, it'll be more of an adding or subtracting aspect of it. Just like you would add or subtract on the number line. That's what you would do with these vector quantities, is that you would add or subtract them on the number line. Further defining the scalar and vector quantities. Again, scalars are those that have just numbers, no direction. Distance. Time is the best one. I really like the time and temperature as examples of scalar quantities. Because a lot of times we can add distance and we just add a direction to it, all of a sudden it changes into a vector quantity. We could also maybe add in volume, mass to those as well, because they would be scalar quantities. Mass even just almost sounds scalar. How would you make the measurement of mass? You'd put something on the scale. Scalar quantity. Quantities that have both size and direction, or direction and magnitude, oh yeah, is our vector quantities. They have arrows. They have arrows, and those arrows mean something. On the next slide, we'll show you what we mean by that. So vector quantities have some arrows. The book, and as I draw some of these out, are going to have different colors. Green is for displacement. Red is for velocity. Purple for acceleration, and forces are blue. There are other colors to represent other vector quantities, but these are the four that we use the majority of the time. So no reason to expand or worry about other things. And especially when we get into start writing in some examples, it will be easiest for us to draw it out, as it's always going to be the suggestion, and drawing it out in the right colors. And when it comes to vectors, we can't add colors together. Green arrows can only be added with green arrows. Red arrows can only be added with red arrows. It helps us make sure that we're making the right additions. Making sure that we're adding the correct things together. when we do add our vectors together, they give us what is called the resultant. The resultant is the answer, so to speak. What you're solving for, the resultant. One thing I think would be very helpful for us that you will want to star, arrow, make sure bold it, is to indicate how do we solve the resultant. And that is, the resultant always points from the tail of the first vector, your starting point, the tail of the first vector is your starting point, to the tip of the last vector. The tip of the last vector would be considered your finish. Therefore, allowing you to say the shortest path. The shortest path. The resultant is, again, the shortest path to go from your start to your finish. Such as the example in the picture. From your house, you go to the store. 5 meters, could be 5 kilometers. The distance is arbitrary, meaning it doesn't matter. And then you go to your aunt's house. Maybe it's 2 kilometers or 2 miles or whatever it is. The resultant would be going straight from one to the other. Now, this is in a straight path. The numbers are going nicely in one direction on a number line. If we looked at things on a Google map, that's not how life works, is it? If you look at it on a Google map, it would have more of a kind of a cross section. What happens if you went 5 meters and then 2 meters? The shortest path isn't 7 meters anymore, is it? It's much different. Now you got a triangle involved, right? Which means we'll need different kinds of math. We'll worry about that later. That's for another time. We'll just worry about things moving in a straight path for now. As I said earlier, it is a good practice to make and draw out what is being found. You will find it when it comes to your equations that sometimes it's not going to be nice and straightforward. Sometimes you're going to need to draw it out. Having some scratched paper to draw out what you are being asked, since many of us are visual learners. We need to see what's happening. If I just said a car drives down the street, stops, and then turns left, okay, most of us could probably envision that. But what you're doing is you're envisioning it in your head. That doesn't translate to the paper very well. What you then do is the car drives a certain speed or distance, turns left, drives a speed into a distance. Now all of a sudden, you're like, oh, I see what I have to do there. And so therefore things are done a little bit differently. If an object is dropped from something, goes a distance, hits something, then bounces up, now we can see, oh, things are different. Now my resultant my start to my finish. So things change. It might be, that's why drawing out what we do is so important. So that you can visualize and make sure when you say, I don't understand this, or I'm not sure what it's asking, if you have something drawn out, it allows me to kind of see what you're thinking. Because otherwise, it's just going to be, I have no idea what you're thinking. I know what the problem's talking about. And even sometimes, because it's been years since it's been a year since we've done this class, I sometimes have to redraw it out. Okay? If I draw it out, that means it's really good idea for the student to draw it out. Because it's good practice.